tahniah. Siaran langsung ini dibawakan khas kepada anda oleh Akademi Youtuber Malaysia. Tumpukan perhatian anda. Siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Hi, Salam, Sejahtera, dan good evening everyone. Welcome to Pusat Tuisyen Akademi Youtuber with the joint venture of EDD Malaysia and Grab Guru Malaysia. So as yesterday is National Day, I think it's not too late that I wish all Malaysian happy National Day. So I am here that to wish our country continue, maintain our peaceful and well-developed. Okay, I am Mr. Peh. Currently, I am teaching at College Tingkatan 6 Tun Fatimah, Melaka. I am the teacher on duty for this week. So for information, we have 2 classes of Physics SPM for this week. So for Form 4 Physics, which is in Non-DLP, okay, will be conducted by Cikgu Rosemawati with the topic of 3.2 Hukum Kepler. Okay, and then another class will be today, where will be SPM Physics Form 5 in DLP. So the topic we are going to continue for this lesson will be 4.2 Electromagnetic Induction. Okay, so we are continue our chapter 4 Electromagnetism with the subtopic of 4.2 as mentioned just now. It will be electromagnetic induction. So in today's learning standard, we have about 4 learning standards. Okay, so I'm here and together with Jimmy. Okay, so Jimmy, welcome. Thank you for continue support me for this week also. Okay, so as mentioned just now, we have about 4 learning standards. So this is learning standard 1, so which is regarding describe electromagnetic induction in straight wire and solenoid. Okay, so for information, so the link ECG will be provided at the end of the lesson, and you have to fill out the link within 30 minutes, just after the class finish within 30 minutes, and you can using any email you are available to fill out the link. Okay, so without further ado, let us continue our learning standard 1. Okay, so first you'll be regarding the definition of electromagnetic induction. So you may look at the slide here. So the electromagnetic induction is the production of induced electric current. Okay, so the current produced we know as induced electric current in a conductor, which is in a changing of magnetic field. So that means that the conductor produce electric where we know as the induced current because of the changing of magnetic field. Okay, so electromagnetic induction produce EMF, which is known as the electromotive force, E, M, and F here. Okay, in a conductor where there is a relative motion of the conductor across the magnetic field. Okay, so here to let the changing of magnetic field happens, so there will be need have the relative motion between the conductor and the magnetic field. Okay, so the conductor can be classified to 2 types we are going to discuss today. One will be straight wire, another one they will be solenoid. Okay. Okay, so the relative motion or conductor, a closed magnetic field can be produced by, first, it will be straight wire, just like I mentioned to you now. So moving a straight wire quickly across the magnetic field between two poles of magnet. So here the two poles here will be south pole and north pole. Okay, so between the magnet, it will be have a magnetic field. Okay, so the moving of a straight wire, you can just look at the picture here. Okay, so when the straight wire moving at the perpendicular position to the magnetic field line, okay, so it may cause the cut of magnetic field, and this we know as a changing of magnetic field, and this may produce EMF, electromagnetic force, and cause the induced electric current to produce. Okay, so another one, it will be moving of a permanent magnet, so it will be just like this figure. So the motion of the permanent magnet towards one end of the solenoid. So solenoid will be represented as a coil wire with red color here. Okay, so we will discuss more detail later on. So if you have any question, you may just ask me in the chat room. Okay, so here we have one important information regarding the production of induced electric current. It will be the changing of the kinetic energy. So where here will be related to the relative motion of the conductor. So either in straight wire or solenoid. Okay, when there is a changing of magnetic field, so the kinetic energy will be converted to electrical energy. Okay, so this will be vice versa for what you learn in the subtopic 4.1. Okay, so the electric current produced and cause a force produced. Okay, so here the electromagnetic force that is produced, we know as an induced EMF. Okay, so here, what is the EMF? So actually you learned already at the subtopic 3.3. Okay, so the electromagnetic force is defined as work done by a source, such as a battery, in driving a column of charge around the complete circuit. Okay, so that means that when we providing a source of energy, such as battery, so the work done will be cause a electron to move. Therefore, the current will be produced when there is a flow of electron. So in here, the induced EMF will be produced when we have the changing of magnetic field. So the EMF induced will cause the electron to flow. So the induced current will be produced in our subtopic today. Okay, so each time the straight wire cut across the magnetic field or permanent magnet, so move towards a solenoid. So here we have two conditions. So you can see here we have a straight wire. In this case, to cut the magnetic field. Then the second case here will be the permanent magnet moving towards a solenoid. So both of these example will be the induced EMF to produce caused by the changing in magnetic field. And this may cause the induced current to produce. And the currents may cause the deflection of sensitive galvanometer. Okay, and this current we know as the induced current. Okay, so basically, this is a theory related to magnetic induction. Okay, so here, let's discuss the first electromagnetic induction, where will be occur in the straight wire. Okay, so the first magnetic flux is formed between the two poles of the magnet. So here we have two poles of magnet, north and south. Okay, so between two poles, you can see we have a black color arrow. we have a lot of black color arrow, and this is known as the magnetic flux. Okay, so the magnetic flux refer to the magnetic field line with this magnetic field line that pass through the surface of air. So here we have a surface. You can just imagine we have a surface with label A. Okay, so here this will be the experiment related to our activity 4.10A at the textbook page 149 to 150. Okay, is to study the electromagnetic induction in the straight wire. So the experiment instruction or procedure you may just refer to textbook. Okay, so here by moving the wire down where you can see in this picture. Okay, so we have 4 directions are going to move for our copper rod, okay, which is represented the straight wire here. So we can go to position B, which is downward, and then another position where the magnet moving upward. So over here. So we have to see, or we have to observe whether the galvanometer pointer will give any deflection. Okay, so here by moving the wire down or magnet upward. Okay, so here you can have 2 different motion. So here firstly you can moving down the wire. Second, you can moving up the magnet. Okay, so the magnetic flux will be cut through. Okay, so here the induced current is produced. Okay, induced current is produced, and is caused by the wire cut through the magnetic flux. Okay, so you can just look at this figure. So the arrow here, we have a red arrow up and down. So if we moving our copper rod down or up, so it's actually cutting the magnetic flux. Okay, because the motion of the conductor or the copper rod here is perpendicular to the direction of magnetic field. So here the magnetic field is cut, and we can know as a changing of magnetic flux, and the induced EMF will be produced. Okay, so here the existence of the induced current is detected by the galvanometer. So where you actually can see the deflection of the pointer of galvanometer when the motion of the copper rod here moving up and down. Okay, so the direction of the current induced depends on the direction of the motion. Okay, either the conductor or magnetic line. Okay, so here for direction A, so here I means that the wire is moved outward. Okay, so the magnet is stay stationary. Okay, so you can see the pointer of the galvanometer deflect to the left. Okay, this will be deflected to the left. Okay, so for direction B, where the wire is moving downward. Okay, so the magnet, that means here, this magnet, the in gray color one, okay, is stationary. Okay, so here the deflection will be showing to opposite position. Okay, here showing that the current flow is in opposite direction. Okay, so the galvanometer pointer deflect to the right. Okay, so if the experiment we conducted by moving the copper rod, okay, to position D or C here, so the position here is actually parallel to the magnetic field line. So the magnetic field line will be here. Okay, using the blue color. Okay, will be here. So you can see the motion of the copper rod or the conductor or the straight wire in position C and D is actually moving horizontally. Okay, and when it will be parallel to the magnetic field line. And this will be not cutting the magnetic flux. And there will be no any deflection at the galvanometer. So this means that no any induced current is produced. Okay. So in conclusion, through this activity 4.10a, okay, so the motion of the wire or here is a copper rod must be perpendicular to the direction of magnetic field. Okay, so here this figure showing that the position of C and D, where these two positions is actually moving horizontally and where they are moving parallel to the magnetic field line. And here will be no showing any cutting of magnetic flux and the induced current is not produced. Okay, so here we have also the Cikgu Hasnitah. Okay, so happy National Day to you. Thank you, Cikgu Hasnitah, for supporting me tonight. Okay, so let us continue our discussion regarding the electromagnetic induction in solenoid. Okay, so the solenoid is actually, you can just look at this figure. So it's a coil or wire. Okay, so when a bar magnet, will be this, is moved into solenoid. Okay, so the magnetic field line are cut by the solenoid. Okay, so that means here, when there is a cut of the magnetic field line, so there will be have a changing of magnetic field line. Okay, so this may cause the induced EMF. Okay, so just now I also explained already, the EMF is actually the work done by the source of energy to move electron. So the motion of electron or flow of electron may cause the electric to produce. Okay, however, here for 4.2, there will be no any source of energy provided. That means no any battery will be provided for the coil wire or in the straight wire. Okay, so how the EMF or the work done able to cause the electron flow? Here, the source of energy comes from the cutting of the magnetic flux, or we know as a changing of magnetic field. Okay, so where the induced EMF will be produced at the both end of the coil wire here. So we know as a solenoid. Okay, so the cutting of the magnetic field line causes the electromagnetic induction to occur. Okay, so an EMF is induced across the solenoid. So where will be at these two ends of solenoid. Okay, and this will be produce the induced current because of the motion of the electron. Okay, so here for the 4.1, the source of energy is provided to flow the electron. Okay, so the electric current is actually provided. However, in 4.2, okay, so where we discuss about the theory of electromagnetic induction is actually we want to create our own source of energy, okay, by changing our magnetic flux. Where if we using the straight wire motion must be perpendicular to the magnetic field line. While for the solenoid, okay, so the magnet just need to move towards the solenoid and cause the cutting of magnetic flux, or just now I mentioned again, this will be known as the changing of magnetic flux. So the induced EMF may produce and cause the induced current to produce in the circuit, and this may indicate by the diffraction of the galvanometer. Okay, so the galvanometer pointer shows the diffraction. Okay, you see here, initial, the pointer is at the center. Okay, at the center of the galvanometer. So this diffraction to the left showing that, so the induced current is produced in the circuit when it is complete. Okay. Okay, then the next here, we discuss the activity 4.10b actually. Okay, so it's regarding the electromagnetic induction in the solenoid. Okay, so here, so when the bar magnet is pushed into the solenoid, okay, you can just imagine in this figure. So when the bar magnet push into the solenoid, so the magnetic flux linkage in the solenoid increases and the current is induced. Okay, so number 6, the galvanometer shows the positive reading. The current is produced in the particular direction in the solenoid. Okay, if I say you imagine the EMF, the GIF here. So with this, okay, so here you can see when the magnet move towards the solenoid, the pointer will be showing to positive. And when moving out from solenoid, it will be showing negative because the current is flowing in opposite direction. Okay, so number 7, when the bar magnet is moved out from solenoid, so the magnetic flux linkage in solenoid is decreases. And the current is induced in opposite direction. Okay, can you see the difference? So I repeat again at the sentence number 6. Okay, at the sentence number 6, so the galvanometer showing positive reading when the magnet is moved towards the solenoid. Okay, and this will be increase the magnetic flux linkage and showing positive direction, okay, in the galvanometer. Okay, and then when moving out from the solenoid, the magnetic flux linkage in the solenoid will be decreases and showing the opposite direction. Okay, and it will be showing a negative diffraction in the galvanometer. Okay, so the galvanometer showing negative reading, the current is produced in the opposite direction in the solenoid. Okay. Okay, then the next here, you can see also the GMF. When no motion, there will be no current induced. Okay, so here, we continue to discuss the activity in 4.10b. Okay, so when there is no induced current is produced when no change in magnetic flux in the solenoid. Okay, that means when there is no motion or no relative motion between the magnet and the solenoid, so there will be no any cut of magnetic flux occur inside the solenoid, and there will be no any induced current will be produced, and the galvanometer will be showing 0 reading. Okay, therefore in the solenoid, current is induced when there is a relative motion between the solenoid and the magnet. Okay, so here we continue to discuss what is the meaning of relative motion to produce induced current in the case of straight wire or solenoid here. Okay, so here, whenever there is a relative motion between the conductor and magnet, so the conductor cuts across the magnetic flux, magnetic line of force and changes the magnetic flux. This one is actually we highlight just now. So when there is a relative motion, there will be cut off the magnetic flux and produce induced current. Okay, so here will be the mechanism to the production of induced current or induced EMF in the straight wire. Okay, so motion or moving of magnet into stationary solenoid or moving the magnet over a stationary wire. Okay, so here we have 2 cases. So first, the magnet is moving while the solenoid is stationary, or the moving of the magnet over a stationary straight wire. So both of these is considered relative motion. between the magnetic field together with the conductor. Okay, so the second here, moving a wire or solenoid move over a stationary magnet. Okay, so here we can move conductor, but the magnet is stop moving. Okay, then here, moving magnet and wire in the opposite direction. So it's also consider the relative motion. Okay, and then here, moving the magnet and wire or solenoid in same direction, but at different speed. Different, you have to add on different speed. Okay, so 4 of these cases will be considered the relative motion where able to produce the induced current. Okay, so the first, the magnet is in stationary, or the magnet is in the first case here will be the moving of magnet in stationary solenoid, moving magnet over a stationary wire. So the second will be vice versa. Then the third, the wire or solenoid is moving at the opposite direction with the magnet. And then the last here, this will be same direction motion between the magnet and conductor, but the speed is different. So therefore, if the conductor and the magnet is moving in the same direction and same speed, we consider there will be no any reactive motion and the induced current will be not produced. Okay, so we have already finished our learning standard 1. Okay, so let us continue the first question here. So is the objective question in 2009. Okay, you may share your answer in the chat room so that we can discuss together. Okay, so let us read the question first. Okay, so diagram 24 shows the conductor. So the conductor will be placed between the two magnets. So here we have actually the wire can be at the SY direction, then PQ, and also WV. Okay, so which action produce an induced EMF in the conductor? Okay, so here we must make sure that the relative motion between the conductor and magnetic flux is actually occur. Okay, so here we have 3 positions. Okay, so the first, moving the conductor along W and B will be here. Moving left and right. Okay, so here the magnetic flux is actually from north to south. So you can see when moving at the WV direction, it is actually parallel to the magnetic flux. Okay, so there will be no any cut of the magnetic flux here. Okay, so then the next, here we move our conductor at PQ direction. Okay, so PQ direction will be here. Okay, so the magnetic flux, as I mentioned, will be from north to south. It is actually perpendicular to each other. So we expected here is consider the relative motion between the conductor and the magnetic flux. So the induced EMF will be expected produced at this position. Okay, and then we see the next position, it will be at the XY direction. So it'll be here. So it will be moved at parallel to the magnetic flux also. So that means there will be no any induced EMF will be produced now. And the last one, moving of conductor and the magnet together at the PQ direction. So that means both of the magnet and conductor is moving at the same direction and same speed like here. So that means here will be also consider no any relative motion. Okay, so answer is very clear. Yes, Jimmy, well done. Okay, so answer here is actually B. Okay, so the answer from Jimmy is correct. Okay, so it's B, good. Okay, so the next will be our learning standard 2 of subtopic today. Okay, so it will be need to explain factor that affects the magnitude of the induced EMF. Okay, so here you need to define the Faraday law. Okay, so the Faraday law will be this. Okay, so the magnitude of the induced EMF or the electromagnetic force is directly proportional to the rate of the change of magnetic flux or the rate of cutting the magnetic flux. Okay, so that means here the induced EMF, okay, so will be directly proportional to the rate of change of magnetic flux. So that means here how we can increase the rate change of magnetic flux or the rate of cut the magnetic flux is directly proportional to induced EMF produced. If the rate is higher, so the induced EMF will be higher. And the induced EMF, just how we mentioned already, is the work done to moving the electron, okay, in the conductor here and cause the current to flow. And the current will be able to measure through the galvanometer. Okay, so where will be in the unit of milliampere or ampere. Okay, so if there is a higher of the rate change of magnetic flux, so definitely the reading of the galvanometer will be increases. Okay, so now we have to discuss how we can increase the change of magnetic flux, or we can increase the cutting of magnetic flux right here. Okay, so here we have actually many factors. So here will be the 5 factors. It may increase the induced EMF. Okay, and this can be measured by the production of the induced current. Okay, so the galvanometer is used to measure or showing that there is a presence of current flow. The current here will be induced current. Okay, so the first, increase the speed of the relative motion between the magnet and the wire. So that means if we can increase the relative motion between the wire together with between the magnetic field line, okay, or we can increase the motion of the magnet towards the solenoid. Okay, so the cut of the magnetic flux can be increases, and this may increase the induced current produced. Okay, then the second, you can see here, we can increase the strength of the magnetic field. Okay, so how we can increase the strength? We can using more magnet. Or you can see, we can increase the numbers of magnet, and second, we can using one magnet, but the magnet will be stronger magnet. So both of these method able to increase the strength of magnetic flux. Okay, and then the next will be increase the length of conductor. Therefore, if for the solenoid, we actually can increase more numbers of turn of the solenoid. Okay, so if there is more turns, so the length of the conductor is actually increases. In the case of solenoid, definitely, if let's say we're using the straight wire, we can using the longer or straight wire so that the induced EMF can be increases. Okay, then here will be another one. We can using thicker wire. Okay, because the thicker wire can reduce the resistance, so it may cause more current to flow. Okay, so here will be the checkpoint for the learning standard 2. Okay, so you also can again show your answer in the chat room so that we can discuss together the answer here. Okay, so let us go through the question together first. Okay, so diagram 27 shows the current is induced when a magnet moves towards a solenoid. Okay, you can see here. So the magnet is moving towards a solenoid and cause the induced current to produce. And this may measure by using the galvanometer, where we actually explained just now. Okay, so the magnitude of the current increases Okay, so here we discuss about how we can increase the induced current. So just now we have already discussed few of the factor. Okay, so the first, reactive motion is reduced. Okay, this must be wrong already because we need to increase the reactive motion where we can increase the speed. Okay, so here must be increased. So here we wrong already. We need to increase. Okay, so the numbers of turn, just how we also mentioned that we should be increase the turn also. Okay, then the next C, magnitude of the magnetic strength is reduced. Okay, this also wrong already. So we need to increase the strength by using more magnet or using the stronger magnet. Okay, so resistance of coil wire is reduced. So this one is correct as we can using bigger diameter of the wire. Okay, so here the magnitude of the induced current increase when the speed of reactive motion increase. Okay, then the strength of the magnetic field is able to increase by using more numbers. Okay, and then the resistance wire can be reduced by using bigger diameter. So the answer here, yes, Jimmy, you are right. So the answer here is actually D. Okay, good, well done, Jimmy. Okay, so here the next question is also the objective question in past year question actually. So this will be the question in 2014. Okay, you may also show your answer in the chat room. Okay, so the question will be like this. Diagram 33 shows an induced current flow in a wire which is moved between two magnets. Okay, so here is actually the straight wire. Okay, the straight wire moving between the two magnets here. Okay, so here, which step will increase the magnitude of the induced current? Again, this will be the question asking you the factor affecting the induced current. So here what we can do to increase the readings of the galvanometer here. Okay, so here, use wire with smaller diameter. Okay, again, just now we explained already, we should using bigger diameter so that the resistance can be reduced, right? Okay, then the second, increase the distance between the two magnets. Okay, so this, is it correct? Okay, so the distance must be closer, okay, so that the magnetic field strength can be increased. Okay, so here, wrong already, we have to decrease. Then move the wire horizontally. Okay, so here also wrong. Okay, so when we move our wire horizontally, that means that the motion between the wire and magnetic field will be parallel, where this will be considered not in reactive motion. So here also wrong. So we should using stronger magnet, so the magnetic field strength can be increased. Okay, again, Jimmy showed the correct answer. Okay, good. So again, here will be the tips. So where just now I explained already, so the diameter of wire must be larger. Okay, so the distance must be closer between two magnets, and the speed of the reactive motion must be increased. So where we can increase the speed now, but here is we not discuss about the speed, we discuss about the direction. So here should be vertically. Okay, so here should be vertically, and we can using stronger magnet. So answer here is very clear, should be D lah. Good, Jimmy. Okay, so here we continue our discussion. Following standard 2 also, the factor affecting the induced EMF and induced current. Okay, so it's a question in 2011. Okay, so diagram 30 shows the magnet which is released from the height at a height and enter a coil when which is connected to galvanometer. Okay, so here we want to see again. Okay, so where we can increase the galvanometer reading, right? So here that means we want to increase the EMF lah, and also the induced current flow. Okay, so the first, the polarity of the magnet increases. Okay, so here is actually not related to the polarity. Okay, Then second, the turns of the coin is set further apart. Okay, so here also not related, right? So because we need to bring it closer, then the cross-sectional area of the wire increases. Okay, so because of here we want to study the height. So we should put higher or lower, right? Okay, so here we need to understand about the transformation of energy. Okay, so where the gravitational potential energy will be actually changed to kinetic energy, and then will be changed to electrical energy. Okay, so the potential gravitational energy, the formula we use will be mgh, and the kinetic energy here will be the formula 1/2 mv squared. Okay, as we explained already just now, when the speed increases, so the induced current produced will be increases. So that means here when kinetic energy increases, the electrical energy will be increases. And how we can increase the kinetic energy is related to the gravitational potential energy provided. So when the gravitational potential energy provided increases, okay, so the kinetic energy will be increases. So what's the relationship between gravitational potential energy and kinetic energy? So this will be mgh equivalent to 1/2 mv squared. So as we explained just now, when the speed increases, so the electric current produced will be increases. So you can see from the formula, the V and H is actually directly proportional. Okay, so again, the Jimmy showing the correct answer. So here when the height or H here increases, so the V increases, then cause the more current will be produced. Okay, so where is related to, we want to release the magnet from high position. Okay, so good, Jimmy. So answer here will be D also. Okay, so as per mentioned just now, when the magnet is released from higher position, the magnet will be moved faster. The rate of cutting of the magnetic field is greater. So the induced current produced will be increases. Okay, so answer here is D. Okay, so good. Or Jimmy to show the correct answer again. Okay, so we continue our third learning standard. Okay, so here will be determine the direction of the induced current in straight wire and solenoid. Okay, just now we already understand that how we produce the induced current, where the concept is very easy. We'll be using the concept of electromagnetic induction. When there is a cutting of magnetic flux or changing of magnetic field, so the induced EMF will be produced and cause the induced current produced. Okay, so now the current produced, we can, using the gravitometer, indicate the magnitude. And you can see just now we also explained some time for certain direction, the pointer will be showing to right, and a certain position it will be showing to the left. Okay, so actually we can using two theory to indicate the direction of current flow in the straight wire and also the solenoid. So for the straight wire, we actually using the Fleming right-hand rule. Okay, so for the section 4.1, so when we producing the force by providing the source of energy, so we're using Fleming left-hand rule. So this will be reversed for the subtopic you learned in 4.1. Okay, we're using Fleming right-hand rule for the direction of current flow in straight wire in the production of induced current through the concept of electromagnetic induction. Okay, then for the solenoid, so the direction of current flow, you can using the Lenz law, okay, to determine the direction. Okay, so here will be the detail. Okay, so here we need to understand the Fleming's right-hand rule. Okay, as per mentioned just now, it is the theory we use to determine the direction of the induced current flow in the straight wire. Okay, so here the fingers we're using will be these three. Okay, so the thumb is actually showing a direction of the motion, moving up or down. Okay, so the motion will be the thumb. Then the first finger will be showing a direction of magnetic field. Okay, so the magnetic field direction will be moving from the north to south. Okay, and then the middle finger or the second fingers here will be showing the direction of current we produce. So we want to indicate the induced current direction through Fleming right hand rule. Okay, so it is very clear showing by the figure here. Okay, so the thumb showing the direction of motion. Okay, then the second finger, the first finger will be showing the direction of magnetic field, where it will be from north to south. Okay, you should actually clear already. Where you learn at learning standard, you learn at the subtopic 4.1, just you using the left hand. And here we instead by using the right hand today. Okay, and then the second fingers here will be direction of the current. Okay, so here the right hand is held with thumb, forefinger. Okay, so forefinger will be the first finger, just like I explained to you. And the middle fingers will be the second finger. Okay, so they are right angle to each other. Will be here right angle, and here also right angle. Okay, so the thumb will be pointed in the direction of the motion. So the fourth finger, or just like I mentioned, first finger will be showing the direction of the magnetic field. Then the middle finger or the second finger will be shows the direction of the induced current, where we're using symbol F for the motion, B for magnetic field, and then induced current by using a symbol I. Okay, so then the second law we learned here will be the Lenz's law, and just now we mentioned that this will be the law where we use to determine the direction of induced current flow in the solenoid. Okay, so the Lenz's law is used to determine the magnetic polarity at the end of the solenoid when the current is induced. Okay, so what means by this? Okay, you can just look at this picture, this GIF. Okay, so the Lenz's law stated that an induced current produced always flow in a direction so that opposes the changes of magnetic flux produced by induced current. Okay, so what means by this? Okay, so that means you can look at this figure. When the magnet moves towards the solenoid, so the direction of the current flow may cause the pull created by the solenoid to against the motion. So this may be explained like when the magnet move towards the solenoid, so the solenoid will be creating a certain direction of the current flow and cause the certain pull produced and against the direction. Okay, so here can be discussed in two cases again. So first will be when magnet is bring towards the solenoid, as mentioned just now. So here you see in this picture, so the south pole of the magnet is moved towards the solenoid, and the current will be produced because of the cut of magnetic flux. Okay, so the direction of current flow in this way will cause the repulsion towards the magnet, because you can see direction of the magnet is moved towards. So the current flow direction due to the cut of magnetic flux may cause a repulsion. So the repulsion will be causes the magnet away to the solenoid. And how we can cause the repulsion? So the magnet at the pole pointed to the magnet must be at the same pole, where will be south. Okay, so here south, another side will be north. Okay, so here will be the explanation. So the induced current produced will be showing by the arrow here. Produce a magnetic flux opposes the motion of the magnet entering the solenoid. Okay, so here will be cause a south pole to produce. Okay, so determine the direction of the induced current in the solenoid. Okay, so here we're using the right hand grips rule. Okay, so right hand grips rule will be this. Okay, so the thumb will be showing the direction of the north, and then the other finger here will be showing the direction of the current. Okay, you can see from this figure. Okay, so here will be the direction of the north, and then other finger will be showing a direction of the current flow. Okay, so we're using this rule to determine the direction flow. Okay, so here, as per mentioned just now, okay, so when the magnet moves towards the solenoid, the opposite motion will be created. Okay, so here the opposite motion, that means that they must be have the same pull. Okay, so when here we have the south, another side will be north. So if you're using the right hand grips rule, so your thumb will be moved, will be showing or pointed to the, if I say you just look at the picture, okay, so will be moved to the left. Okay, move to the left. Okay. So because when both here south and south at the solenoid and south at the north pole, okay, also we must using same pole causes a repulsion to occur. Oh, you see, south pole is produced at the end of solenoid against the south pole of the magnet to move into solenoid. Okay, so if you're using the theory we learned, okay, so be like this. So your hand will be shown like this when other finger showing a direction of the current. And here you see, we know already our thumb must be shown at the right position. So your another four fingers will be go up, just like what is happening here. So the current is flow upward because of the north is at the left side. So just using your right hand to show. Okay, if I say you see my hand, it will be opposite lah. So it's better you just observe the figure I show you already here. You can see, very clear. So firstly, your thumb must be pointed to the left side. Okay, just like a figure. And your other finger, you may observe it must be moved outward so that you can just know the direction of current. Okay, in this way, so there will be the south pole for the solenoid at the right side, where it will be against the motion for the magnet to move in. Okay, so this is what we according to the Lenz's law. Okay, so the second case will be when magnet is moving away from the solenoid. Okay, it will be just like this. Okay, so again, moving outward. Okay, so induced current produces a magnetic flux that opposes the motion of the magnet. Here should be move up the solenoid. So when the magnet moving up, so the direction or current flow may cause the end of the solenoid have an unlike pull with the magnet pull here. So that means when we moving up the magnet from solenoid, so the Lenz's law tell us that the current flowing direction may cause the end of the solenoid have the opposite pull, where here will be north lah, so that the attraction will be occur. Just now when magnet moving in, so the current direction flow at the end of solenoid at this position must be cause repulsion. Okay, so the motion between the magnet and the solenoid will be opposite. Okay, so here when the magnet move up, the end of the solenoid may cause the magnet to moving in. So where here will be the attraction. So when attraction, so the pull at the end of solenoid and the magnet, pull of the magnet towards the solenoid must be opposite. Okay, so here the attraction must be occur. So here will be north, another side will be south. So our right hand, again you use your hand, not see my hand, these will be opposite. Must be pointed your thumb to the right. And you see again your other fingers supposed to be moving down. Okay, again, just as I mentioned to you, here will be north, where we have the same, unlike pull with the end of the solenoid and pull of the magnet. Okay, so just as I mentioned already, unlike pull, so the attraction may be occur. Okay, so the induced current flow in a direction, as mentioned in the diagram here, okay, to produce a north pull to attract the magnet from the moving away from the solenoid. Okay, so you can see here, this will be your hand, right hand. So your thumb must be pointed to the right, and you can see your other finger should be moving down, just like the diagram I show you here. Okay, okay, so you can see the direction of the pointer of galvanometer will be opposite lah. Okay, so here we'll be going to test you whether you understand the discussion just now we discussed about the direction of the straight line, a current flow in straight line, and also the solenoid using the right hand gives rule for the Lenz's law, and then the Fleming right hand rule to determine the induced current flow in the straight wire. Okay, so here the question number 5, where is the example question of 2013 Okay, so the diagram 23 shows the process of producing an induced current in the wire. Okay, so here this process is explained by, so what is the theory able to determine the direction produced by the straight wire here. Okay, so here we have A, Hooke's law, B, Fleming right hand rule, C, Newton's third law, and then the last here will be the right hand gives rule. Okay, so if you have the answer, you may show in the chat room also. Fleming right hand rule. Okay, this is the answer from Jimmy. Okay, so let us see whether the answer is correct or not. Okay, yes, the answer is correct. You see the direction of the induced current in a conductor can be determined by using Fleming right hand rule. Here the conductor means the straight wire. So answer here is correct. Answer is B. Okay, and if let's say you're using the Fleming right hand rule, you may get that the current direction is just like the arrow I show you here. Okay, so here your right hand will be this. Okay, but I think that my finger's direction will be opposite will be opposite. Okay, so here the thumb is actually showing a direction, showing a direction of motion. Your thumb will be here actually. Okay, and then your 4 fingers or the first fingers will be from the north to the south will be here. Okay, so will be like this lah. Okay, but you have to do your own now because direction from my side will be different from your side. Okay, so here will be actually moving in. Okay, it's moving in. You can try yourself. Okay, so answer here very clear will be B. So answer from Jimmy is correct. Okay, so good. Okay, so here will be the another question where is related to the direction of current flow in the straight wire. Okay, again, we using the Fleming right hand rule. Okay, you can just show your answer in the chat room. Okay, so which of the following diagrams show the current direction of the induced current in the conductor? Okay, so here, which is correct? Okay, so the first case, again, we're using our Fleming right-hand rule. Okay, so the first, you can see the motion is go down. So your thumb must be showing down. Your fingers, thumb must be showing down. And then the direction of current must be from the left to right. Okay, from left to right will be here. So again, you'll be opposite direction. If follow my fingers now, I think I show you the picture is better. Okay, so will be almost like this. So your thumb will be showing down. Okay, so your first finger or four fingers will be from the north to the south. You can see your current is moving up. Here is actually moving in. So it's strong. Suppose your fingers, second fingers or middle fingers will be moving up. Okay, so will be this. So here that means the answer A is already. Okay, so we check the second. Answer B. So the motion is moving up. So that means your thumb, using your right hand, your thumb must be moving up. And then the direction of magnetic will be from left to right. Okay, left to right. Then the current is actually you will get moving in. Okay, will be moving in. Again, okay, just on the first one is wrong already. So here your fingers supposed to be like this. Thumb moving up. Then here direction will be from left to right. Okay, you can just look at the figure. Okay, so your current should be moving in should be moving in. Okay, you just observe the hand in the screen, not my hand again. Okay, so you'll get moving in. So you can see from picture, the arrow is moving up. So again, B is wrong already. Okay, so we look at the answer. C, option C, I'll look at the option C. So here, the motion is down, where is showing by the thumb. Okay, then the direction of the magnetic field line will be from left. So from the right to the left already now. From the left to the right. From the right side. Here to the left, to the left. Okay, so will be like this. Down. So the current will be moving in, right? The current is moving in. So we like this. So the picture showing the current is moving up. So C is also already. Okay, so here we have the last option. So the D must be correct. Okay, so again, using your right hand. Okay, will be almost like this. So your thumb moving up. Okay, your direction of B magnet will be from north to south. Okay, from north to south. Okay, so be showing that your current is moving up. So this will be same direction. Okay. So answer will be D. Okay, then the next question. Okay, so the question number 7. So it's an example question in 2016. Okay, so the direction of the induced current is such that the change producing it will be opposites. Okay, so what is the theory here? So here is actually very clear that this will be the Lenz law. Okay, so the Lenz law showing that settled that the induced current flow in the such a direction so as to oppose a change produce it. So here is actually Lenz law. Very clear will be D. Okay, then the question number 8 will be the determination of the direction of the current flow in the solenoid. Okay, so which is showing the correct direction. Okay, so just now I asked you to use the right hand grip rule, right? Okay, so here, the A. So here when the motion of the magnet moving in, so here will be cause repulsion, right? So that the direction will be against the motion of the magnet. So when repulsion, they must be have showing the same direction. Here must be not already. So again, using your right hand, okay, using right hand grip rule, okay. Okay, so here, just like I mentioned to you already, okay, so the current, induced current direction flow must be opposite the change. So that means when magnet towards, it may cause repulsion. Okay, so we're using the right hand grip rule, where we learned already just now. Okay, so here, when we need to cause repulsion, okay, I think this picture is reversed already, because the north is at this side. Okay, so the current flowing will be moving up. Okay, so you can see these two directions is opposite. So answer A is wrong already. Okay, so this picture is actually wrong already. Okay, suppose we using opposite. So this one picture reverse wrong already. So the thumb is actually at the left side. Okay, so here suppose will be like this. Okay, so it's moving up. So the direction is opposite. So wrong already. So B, so you can see here is moving in. So here again, cause repulsion. So when cause repulsion, here should be S. So when here is S, here will be no. So your thumb will be go to the right side. So the current is moving down. Okay, but you can see here is moving up. So here is no also lah. Okay, so here is actually cause repulsion. So must be like Paul just mentioned. Suppose here is north lah. I think I wrong already for the picture. Okay, so here, okay, I think here I also reverse already. So here also reverse already. So I think this picture also wrong. So this picture is wrong already. Okay, so you just using what I tell you just now. So your thumb should be go to the right side for this case. So the picture here is wrong already. So here also wrong. Okay, then C. Okay, so here, when here we have the direction away from the magnet, so here should be attraction. So here should be south. Okay, again, I think this picture is wrong already. Okay, so here should be south, here will be north. So that means your thumb should be go to the right side. We'll be using this picture. Okay, so here the current will be moving down. Okay, will be moving down. Okay, so you can see the arrow is wrong already. Okay, so here also wrong. So answer here supposed to be D. Okay, will be D. Right? So you can just look at the picture again. So here, away, the magnet showing away from the solenoid. So here should be cause attraction. So here will be north. So when here is north, we're using this picture, I suppose. So your thumb should be at the left side. So we'll be moving up. Okay, so here showing that the picture, D is correct, D. Okay, so answer for this will be D lah. Okay. Okay, so again, the picture here should be D. Okay, so answer D. Okay, so I think we can take a break before we continue the learning standard 4. Okay, so take 5 first. See you all later on. Okay, so welcome back. So let us continue our last learning standard. Today's learning standard 4. So here we want to discuss about the design, direct current and alternating current generator. Okay, so here firstly we discuss about the working principle of the direct current DC. Okay, we use symbol DC for the direct current generator. Okay, so basically from the picture you can see here we have a commutator. Okay, it will be here. 2 commutator, split commutator on here, and then we have the carbon, okay, carbon brush, and we have a coin wire. Okay, so we're labeled with A, B, C, D, okay, and it's between the permanent magnet. Okay, and then the direction of current flow here we expected is the DC current and able to measure by using galvanometer lah. Okay, so here will be the first section where you can see A. So when you look at A, so it will be the picture showing here where is the position of the coin wire. Okay, so where it is actually at the vertical position. Okay, the vertical position. Okay, so when a plane of the coin is in vertical position, so the side of AB will be here. Side AB and CD here is parallel to the magnetic field. When just how we mentioned, when there is a parallel position between the conductor and the magnetic field line or magnetic flux here, so it will be no any cuts of the magnetic flux. Okay, so the galvanometer showing 0. So here will be no any induced current produced now. Then for B will be this position. Okay, so be this position. Will be this position. Okay, so here the position of the coin will be horizontal position. Okay, so here will be CD move outward. Okay, move outward, and then it will be from here moving outward, and the AB will be moving downward. So causes the position will be like this. Okay, and here, since this is perpendicular of the conductor to the magnetic flux. Okay, so the cut of magnetic flux is occur and the current will be produced. You can just look at the pointer galvanometer. Okay, so here showing the maximum current. Okay, then at the C position will be this. Okay, so again, so the galvanometer showing the reading is 0 here. Okay, so where again there will be no any cut of magnetic flux occur. Okay, so you can just look at the sentence. After this position, the current starts to decreases until E is 0 when the plane of the coin is in the vertical position. Okay, because the magnetic field line are not cut. Okay, and then here the next in the horizontal position. Okay, so the AB upward. Okay, so now AB moving outward, CD moving downward. Okay, so the cutting of magnetic flux is occur at this position now. Okay, so the maximum current will be produced here. Okay, then the next. Okay, but here the most important point here will be, you can see, okay, so the direction of the current in the external circuit is not changed. It will be here. You see here, this is the external circuit. The current flow for picture B and C is will be in one direction, which is the direct current. Okay, then the E here, the process is repeated. You can see E and A is the same. So they will be repeating the process again. Okay, so at this position, you can see there will be actually no cut flux of the magnetic flux here. Okay, so the current will be 0. Okay, so the current in the external circuit is direct current. So there is the current flow in one direction. Okay, so the second, there will be working principle regarding an alternating current generator. Okay, so here, what's the difference here will be, you can see the ring here we have 2. Okay, split ring we have 2. Just now we have only 1. Okay, and others will be almost the same. We're using the galvanometer again to showing the current flow and the direction of current flow. And here will be considered as an external circuit. Okay, we want to see what is happening here. Okay, so again, you can see A will be the position of the coin. So where is actually vertical position. Okay, so here, the side of AB and CD is moved parallel to the magnetic field line. When they is parallel, there will be no cutting of the magnetic flux. Okay. Okay, so there will be no induced current produced. So the galvanometer is at the middle, which is a 0 reading. Okay, so B will be this. So you can see now the position is horizontal. So the BC is moving up. The CD is moving down, will be like this. Okay, so the side of the BC and AD. BC and AD. Okay, so it is actually AB and CD. AB and CD cut the magnetic line at the right angle. Hence, the induced current and induced EMS produced, where will be maximum. And here, showing the forward current. Okay, why? The direction will be changes actually. Okay, so C will be this position again. So it will be at the vertical position. And at this position, so there will be no cut of magnetic flux. So you can see no induced current is produced. So here will be showing 0. Or for the pointer or galvanometer. So here will be 0. So you can see here will be AD will be here, this side. Okay, then the next here will be the horizontal position again will be here. Okay, so now the CD is moving outward. Here moving downward will become this. Okay, so the side AB and CD is actually right angle to the magnetic flux. This will be cut the magnetic flux and showing the pointer of the galvanometer is deflected. But you can see here the external circuit showing the changes from B is from here to here. Then for the D, the direction is opposite from here to here. So you can see here, the current will be flowing at the reverse current direction. Okay, but the value is maximum. Okay, so the E, you see E and A is actually the same. So the process is repeated lah. Okay, so here the key will be the direction of current in the external circuit changes each time the coin passes the vertical. Okay, passes the vertical position. Okay, so the current in the external circuit here, showing alternating current. So where the position or direction of current is changes lah here. Okay, so here we want to compare the different or similarity between the DC, direct current, and alternating current generator. Okay, basically this is the GIF for DC generator, and this will be the AC generator. Okay, so the similarity first, both applying the electromagnetic induction theory to producing the current. So where they need to have a reactive motion between the conductor and the magnetic field line, so that the changes of magnetic field may cause the induced current to produce. Okay, so where the transformation energy will be connected to electrical energy, where I actually explained already just now. Okay, so the coin is rotated by the external force. So here we discuss about the force causes the cut of magnetic flux and produce the current. Okay, so the coin will be cut the magnetic flux and cause the EMF or induced current to produce. Okay, see, this is what the similarity between the DC generator and AC generator. Okay, then for differences, the first, okay, you can see the end of the coin are connected with a split ring commutator with this for the DC generator. However, for the AC generator, the end will be connected with two split rings. So this is the first difference. Okay, then the second, the two sections of the commutator exchange contact with the brush every half rotation. So that means here, at the first, the Q will be at the left side, then the P will be at the right side. When there is a rotation, when AB changes to here and CD changes to here, the position of P will be changed to left, and then the Q will be changed to right. So the position will be changes. Then for the AC generator, the same ring will be always connected with the same brush for both here also. Okay, then the current flow for the DC generator, there will be only one direction because of the external circuit. Current flow is the same, just like I showed already on the picture. Then the AC generator, they will be at the opposite direction. Okay, so therefore, the output current for DC generator will be direct current. Then output for AC generator, there will be alternating current. Okay, so these are the differences between AC and DC generator. Okay, so now let us go through the question again. You may show you your answer in the chat room. Okay, so diagram 28 shows an electric generator. So here, which graph shows the correct output between voltage and time? Okay, voltage and time. Voltage is actually represent the EMF. Okay, so where the unit is actually the voltage or EMF, induced EMF lah. Okay, so here what you actually need to check. So you need to identify whether this is the DC or AC generator. Okay, so how we know that? You can just observe. Here we have two split ring. Okay, so when we have the two split ring, it will be the AC generator. Okay, so when this is the AC generator, okay, so the current will be, the output current is actually the AC current. Okay, alternating current, and it will be show the sinusoidal graph, so be in sine. So answer is very clear. It will be actually C. Okay, Then the next here, we go for our last question. So the question here is actually the question section C. Okay, so there will be the comparison and the multiplication. Okay, so the question will be like this. So here we have two diagrams, 10.1 and 10.2. Okay, so where both will be dropped at the same height. Okay, so the difference here is very clear that the coin numbers is different now. So the 10.1 is actually less than 10.2. Okay, so before we discuss about the difference between the picture, okay, so just now I saw answer from Jimmy is C. Okay, supposed to be the question number 9. Okay, it's correct. Okay, good. Jimmy, still stay with me here. Okay, thank you for your support. Okay, so let's continue to our last question here. Okay, so here the question number A will be name the physical quantities measured by galvanometer. Just now mentioned already now. So it will be actually used to measure the current. And the current here is actually induced current. Okay, so the answer here will be measure the induced current. Okay, so here we have another teacher, Cikgu LK. So thank you for support me also. Yeah, Sejahtera on. So hopefully you can share more the class link to your students okay, so that more students will be get benefit from my lesson. Okay, so here we continue our question B. Okay, using diagram 10.1 and 10.2. Okay, so we want to compare the firstly here 3 marks. You need to compare 3 different or similarity between these two diagrams 10.1 and 10.2 Okay, so here firstly you need to compare the strength of the magnet. Okay, so here we're using actually the same magnet. So suppose the strength will be the same between the picture 10.1 and 10.2. And then the second here, the turns of the coin, you can see very clear that 10.1 is less compared to 10.2. Then the last here will be the size of diffraction galvanometer here. So initially it will be at the middle. So where will be 0. So the picture at 10.1 showing slightly deflected from 0. Then the 10.2 will be more. Okay, you can just observe through the diagram. Okay, so here the first we discuss about the strength. So both will be the same. Just now I explained to you already because we're using the same magnet. Okay, so it will be 10.1 equal to 10.2. Okay, you're using a mathematical symbol to show in the answer. Okay, so make sure you write the parameter to show the comparison. Okay, let's say you just mentioned 10.1 equal to 10.2, we do know what is the parameter you refer to. And the second will be numbers of turn. Here will be very clear that the 10.1 is bigger, is more than 10.2. You can using, 10.1 is less than 10.2. 10.2 is 4, so we're using this symbol, less than. Again, show your parameter for the comparison. Then the last here will be the size of galvanometer. 10.1 will be less than 10.2. Will be this. Okay, then the next here will be the relationship. Okay, will be 3 marks. Let us go through the question. So state the relationship between the numbers of turn or coin with the size of diffraction, pointer diffraction. Okay, so you can see when turn in 10.1 less, so the pointer diffraction will be less also. Okay, sorry. Okay, so here will be less also. Then the second, we compare the numbers of turn and the rate change of magnetic flux. Okay, just how we assume already, when we have a longer conductor or more coin of solenoid, so the rate will be increases now. So when more coin, the galvanometer will be showing more reading, right? This will be showing by the rate. So here more numbers of turn, rate also increase now. Then the last will be rate and the magnitude. So when rate change increases, magnitude will be increases. So all of this is directly proportional. If you compare the diagram 10.1 and 10.2. So first, the larger the numbers of turn, the larger the deflection. Okay, so this will be the first comparison, first relationship. Then second, the larger the numbers of turn, the higher the rate. So this will be the second relationship. Here. Then the third will be the rate change increases, the magnitude of induced current will be increased also. Okay, so the higher rate of the change of magnetic flux, the larger the magnitude of induced current. Okay, so answer is very clear. For comparison, you can get the full marks. Okay, then next will be the C. Here is normally the theory. Okay, so 3 marks. So you have to give at least 3 points. Okay, so diagram 10.3 shows the point X and Y round around the soft iron core over here. Okay, so when switch S is turned on, the galvanometer deflects to right. Deflected to right. After a while, it will be returned to 0. Why? That means that initially got current. When the switch S is off, switch S is on. After that, 0, that means no more current. Why? Become like this. So you can see that initially there will be no any current flow. So the iron core is not magnetized. So there will be no current flow. So after that, when current is flowing, so in here, so current will be flow in this direction. So may cause the electromagnetism. Okay, it may cause the electromagnetism. So here will be occur the changes of magnetic flux at the beginning. So the induced current is produced. However, you can see that we're using the battery. So the battery will be not showing any changes of direction. So that means the magnitude or current is actually continue to flow. But the direction is not changed. So that means there will be no cut of magnetic flux at the final. Okay, or later on. Okay, so that means the firstly, we have a changes of magnetic causes the change of magnetic flux. So the induced current is produced and cause the galvanometer deflected. Then later on, because we use the battery, so the magnitude maintain the same and the direction is still maintain the same. Okay, so the changes of magnetic flux is not occur. So the induced current is not produced. Okay, so this is two situations you actually need to discuss in the answer. So first, the soft iron core become a magnet when switch S is turned on. Okay, so that is a change of magnetic flux. The induced current is produced. Hence, the galvanometer pointer deflects out. This will be the first situation. Okay, then the last will be SIM using dry cell. So there will be no changes in magnetic flux because the direction is always the same. So when there is no changes of magnetic flux, there will be no current flow. So the pointer will be showing 0. So it is what you can observe through this situation. Okay, so then we go for our last question, 10 marks question. Okay, so here will be the multiplication question. Okay, so diagram 10.4 shows the structure. Okay, so show the structure of the DC current. You can see the ring here, we just using one split ring. Okay. Okay, so the generator produce a small direct current, suggests the modification that can be made so that we can produce high alternating current. Okay, so here state and explain the modification based on the characteristic of the magnet, wire, and the type of ring. Okay, so here since we need to have a 10 marks minimum, right? We need to have a 5 modification, but we have the question just ask you to give suggestion for magnet, wire, and type of ring. If I say one of the character, you just give 1. So total you can just get 3 plus 3, 6. So that means one of the characters should be more than 1 here. Okay, and I advise you to give more than 5 suggestions. So can be give 6 plus 6, 7 plus 7 for the modification. Okay, so here how we change the direct current to AC current. We can actually change our numbers of ring here, right? We have to using the split ring instead of using the one split ring. We have to using split ring 2 instead of one split ring. Okay, so here the commutator is replaced by 2 split rings. Will be just like what we learned just now, right? Okay, so we need to have 2. Okay, so that we can able to generate the AC current. Okay, and then the second modification besides of the type of ring, here we can discuss about a magnet and wire, how we can increase the current flow. So here we need to discuss about a factor affecting the current, induced current produced. Okay, so we can using the stronger magnet so that the strength of the magnetic field can be increases. Okay, wire should be used more turn of the coil of wire, right? And others now. So here we have more suggestion answer. The first, we're using stronger magnet so that to get stronger magnetic flux. Okay, then the next will be we increase the numbers of turn of coin. So here we need to have more coin. Okay, so that we can increase the rate cutting of magnetic flux. Okay, then we can also have other suggestions. Example here, we can widen the coil with soft iron core. Okay, so that we can increase the strength of magnetic flux. Okay, so here is the first suggestion for increase the induced current. Second, this will be third. So here I have prepared another 2 suggestion answer. So the next will be rotate the coin with higher speed. When the speed increases, the rate of cutting magnetic flux is also increases now. You see. Then the last here, we can increase the surface area of coin. Okay, so here the change in magnetic flux involved will be larger. Okay, so here is actually all the reference answer for you. So you can see here we have a 6 suggestion and the 6 reason is more than 5 plus 5. Okay, so that you can get more chances to meet the scheme answer. Okay, and please do not give the contradict answer. Okay, so that's all for my sharing today for the subtopic of 4.2. Okay, so please help to share my lesson to your friends so that more of your friends able to get benefit from my lesson. Okay, and then here I want to give you the link for link ECG for today's lesson. Okay, so I post to the chat room. Okay, so you may actually using any email to fill up. Okay, so please fill up within the 30 minutes after the live finish today. Okay, so please don't forget to follow our next physics classes in every Friday, 9:30 p.m. for the Form 4 physics. Okay, for the non-DLP class, and then for the DLP class, where we discuss about the SPM Form 5 physics for every Sunday, 8:45 p.m. and will be going to be presented by Cikgu Hasnitah for the subtopic 4.3. Okay, so that's all for me today. Okay, so hopefully my lesson today may help you to get more understanding for this subtopic 4.2. Okay, so that's all today. Bye-bye. Thank you for support.